Bluetooth mode. Connected.
स्क्रीन शेयर करें बच्चे। अच्छा रुक जाओ, मैं यहाँ से परमिशन दूंगा। देखिए स्क्रीन आप शेयर कर सकते हो आप। So now you can start your presentation, Ms. Dikshit.
Good morning. My name is Dikshi, and today I am here with my presentation on Stern-Garlach experiment under the guidance of Dr. Sanjay Kumar Singh, Assistant Professor, Department of Physics, SD College, Barnala. Here is a glimpse of things to come. We will discuss about what is Stern-Garlach experiment, objective to perform this experiment, experimental arrangement, and other related topics. What is Stern-Garlach experiment? The Stern-Garlach experiment demonstrated that the spatial orientation of the angular momentum is quantized. Thus, an atomic scale system was shown to have intrinsically quantum properties. Objective to perform this experiment. The Stern-Garlach experiment was meant to test the Bohr-Sommerfeld hypothesis that the direction of the angular momentum of a silver atom is quantized. Experimental arrangement. The substance whose atomic beam is to be studied is kept in the oven. In the original experiment, silver atom was used for this purpose. A beam of neutral atoms, when heated, come out of the opening of the oven. The beam, after collimation by passing through two slits S1 and S2, is passed through a non-homogeneous magnetic field produced by specially designed electromagnets. The outgoing beam is recorded on a suitable detector screen, which for silver is a cold plate. This is a setup image. Here we can see an oven, two slits S1 and S2, beam of silver atoms, two electromagnets, and a detector screen. This is a 3D image. We can see a furnace, or we can say an oven, which is emitting silver atoms passing through S1 and S2. The beam then passes through electromagnets N and S, and then the beam is recorded on the detector plate, which here is written classical prediction. Working when the current when the current in the electromagnet is switched off, the beam strikes at P and produces a narrow trace at the center of the screen. But as soon as the current is switched on, the beam spreads, producing two traces P1 and P2 on the screen. Both these traces are of equal intensity and have same patterns. The spread in the two traces is due to the Maxwellian distribution of velocity of the atoms around some mean value. As each silver atom can possess only two possible values of spin, that is half and minus half, the beam of atoms must split into two beams during its passage through the non-homogeneous magnetic field. The component mu of the magnetic moment of the atom in the direction of the field as studied by Stern-Garlach was found to be 1 Bohr magneton. Theory: consider the silver atom as a bar magnet of magnetic moment nu. When this atom is placed in the magnetic field B at a certain angle to the field, it experiences a torque which is given by tau is equals to mu cross product B. This torque tends to align the silver atom parallel to the field B. Let the atomic magnet, that is silver atom, turns through an angle theta from the field direction, then it possesses additional energy given by U is equals to minus mu dot B, which is equals to minus mu B cos theta. Let the magnetic field B varies along z-axis And suppose the silver atom enters this magnetic field with a speed v along x-axis. Then the force acting on the atomic magnet along z-axis is F is equals to minus curl U upon curl Z, which is equals to curl U dot B upon curl Z, which is then equals to mu cos theta curl B upon curl Z. If mass m be the mass of the silver atom, then acceleration produced in it is given by A is equals to F upon m, which is equals to mu cos theta upon m curl B upon curl Z. If L be the length of the path of the beam through the magnetic field, then time taken by the beam to travel through the field T is equals to L upon V. Therefore, the displacement of the silver atom along z-axis on coming out of the field is given by z is equals to at square upon 2, which is equals to 1 by 2 mu cos theta upon m curl b upon curl z l square upon v square. Z is equals to mu L square cos theta upon 2 mv square curl B upon curl Z. According to the Maxwell's law of distribution of velocities, V is equals to 3 kt upon m whole raised to power 1 by 2, where K is the Boltzmann constant, T is the temperature of the oven, and the value of K is 1.38 into 10 to the power minus 23 joule per coulomb. Then we get Z is equals to mu L square cos theta upon 2m into 3 kt upon m curl B upon curl Z. After solving the equation, we get mu L square cos theta upon 6 kt curl B upon curl Z. This equation gives the maximum displacement of the silver atom at the center of the trace. Special cases: if there is no magnetic field or there is no uniform field, that is curl B upon curl Z is equals to 0. Therefore, we get Z is equals to 0. Hence, there will be no displacement of the atomic magnets along z-axis. Therefore, they will produce a fine straight line on the photographic plate P. If there is non-uniform magnetic field, the atomic magnets will be displaced from their path in plus z-axis direction depending upon their orientations and hence produce a trace on the plate P. Explanation: in the normal state, the whole magnetic moment of silver atom is due to the spin of one of its electrons. In a uniform magnetic field, such an atomic dipole or atomic magnet will experience a torque tending to align it in the direction of the magnetic field. In non-homogeneous magnetic field, each, each pole of the dipole is subject to a force of different magnitude. As a result of this, there will be a resultant force on the dipole that varies with its orientation with respect to the magnetic field. According to classical ideas, the atomic dipole can have any inclination to the magnetic field. So the silver atoms will be deposited on the plate P at all places bounded by the trace corresponding to the values -1 and +1 of cos theta. However, Stern and Garlach observed that the initial beam of silver atoms splits up into two distinct parts corresponding to the two opposite spin orientations in the magnetic field that are allowed by space quantization. Conclusions: if there if either the magnetic field is uniform or magnetic field is zero, then curl B upon curl Z is equals to 0. Therefore, Z is equals to 0. Hence, there is no displacement of the atomic magnets along Z axis. Hence, we find a straight line. If the applied magnetic field is non-uniform, the displacement is either along plus Z axis or minus Z axis, depending upon their orientations, and we get a trace on the plates. Significance: the displacement z of the line from original position derived by the quantum theory is in close agreement with experimental values, and thus the above experiment give experimental confirmation of the interaction of orbital angular momentum and spin angular momentum and their associated magnetic moments, as well as space quantization of total magnetic moment vector of the atom. Some important questions. Question number 1. Why non-uniform magnetic field is used in Stern-Gerlach experiment? Because in uniform fields, there is no net force on the atoms regardless of their magnetic dipole moment. The energy of the interaction has the form U is equals to minus mu dot product BR, which is equals to minus G sigma dot product BR. The force is given by the spatial gradient of the energy. Thus, in a uniform field, there is no way to spatially separate the atoms by their magnetic dipole, which is what Stern-Gerlach magnets are meant to be doing. Question number 2. Why silver atoms were selected for Stern-Gerlach experiment? The silver atoms allowed Stern-Gerlach to study the magnetic properties of a single electron because these atoms have a single outer electron which moves in the Coulomb potential caused by the 47 protons of the nucleus shielded by the 46 inner electrons. But why only silver atoms or neutral atoms were selected for the experiment? Why not ions? This is because Stern-Gerlach experiment was performed to detect the existence of electron spin and magnetic dipole moment of atoms, passing the beam of neutral atoms in a non-homogeneous magnetic field. If the same experiment is repeated with ions rather than neutral atoms, the net charge in the ions will interact directly with magnetic field, though the non-homogeneous field will interact with the dipole moment. But the former effect will be very large than the later, and the basic purpose of the experiment will be defeated. References: Modern Quantum Physics by Ashok Sharma and A.S. Vasudeva, Wikipedia, and other internet sources. I would like to express my special thanks of gratitude to my physics teacher, Dr. Sanjay Kumar Singh, for their able guidance and support in completing my project. I would also like to extend my gratitude to the principal ma'am, Dr. Rama Sharma, for providing me with all the facility that was required. Thank you.
Very good. Nice presentation. Dekhiye, if you have any question, then you can ask. This presentation is open for questioning. तो रुचि ने बहुत अच्छे से इसमें क्वेश्चन आंसर भी कवर अप कर रखे हैं प्रेजेंटेशन में, तो मोस्टली तो क्वेश्चंस कवर हो जाते हैं, है ना। मैं भी इसमें कोई क्वेश्चन ऐसे जनरेट नहीं कर रहा हूँ। आप लोग को अगर कोई क्वेरीज है तो आप लोग इसमें पूछ सकते हैं। So I hope कि कोई क्वेश्चन नहीं है। So thank you so much, Lakshmi.